Hi, I'm Sudeep Pasricha, the Aram and Helga Budak Endowed Professor of Electrical and Computer Engineering at Colorado State University, and I direct the Embedded High Performance and Intelligent Computing Lab. Here's a quick tour of what my lab works on. Our mission is to design better software, hardware, and hardware-software co-design for computing that's energy efficient, fault-tolerant, real-time, and secure at every scale, from a single chip all the way up to global data center fleets. We work across three levels: chip and electronic design automation, IoT and edge systems, and data centers and high-performance computing. So let's go through each of them. First, the chip level, the on-chip networks, memory, and accelerators that everything else runs on. So as processors add more cores and accelerators today, communication becomes the biggest bottleneck in almost any computing system. We design networks on chip for 2D chips, chiplet platforms, and three-dimensional stacks. The work involves developing new topologies, routing protocols for CPUs and GPUs, including deadlock-free, fault-tolerant routing, and reinforcement learning-based traffic management mechanisms. We also build these networks using light instead of electricity with silicon photonics for much lower latency and higher bandwidth chip-scale communication. Our cross-layer designs connect physical constraints in these systems that are related to things like optical loss, laser power, thermal sensitivity, and device control, all the way to the architecture design and runtime management. Beyond networking, we can do the AI computation itself optically. So we have designed photonic accelerators for convolutional neural networks, transformers, graph neural networks, as well as state space models. Instead of moving data to a separate accelerator, we can also compute inside memory itself. And specifically, we've been looking at in-DRAM accelerators for AI workloads. We have explored reconfigurable and mixed analog or stochastic accelerators for large language models and other types of neural networks. This work essentially asks how algorithms and data flows should change when the hardware is fundamentally different from a conventional CPU or a GPU. We also design the memory technologies themselves: 3D DRAM, phase change RAM, optical RAM, spin transfer torque RAM, and how to architect systems that combine their different strengths. Comet, one of our cross-layer optical phase change memory designs, is one recent example. 3D NAND flash has reliability and security issues that most people never think about. So recently we've showed rowhammer style vulnerabilities exist in flash, and that erased data can sometimes still be recovered from sanitized flash. We also look at approaches for computing within flash memory. Security runs through nearly everything that I've shown so far, but it's also its own direction, securing AI accelerators, on-chip networks, and flash from the ground up, like our safe flight defense for optical convolutional neural network accelerators. This is one of the fastest growing parts of our lab. Great hardware also needs smart software on top. So we build resource managers that decide what runs where on 2D and 3D processors and heterogeneous accelerators, like Moela, our multi-objective evolutionary design space exploration framework for 3D many-core platforms. Next, one level up, we get to embedded IoT and edge devices, where computing interacts with people and the physical world. Real-time response, robustness, security, energy efficiency all become important here. Now, you probably know that GPS doesn't work indoors. So we build AI-driven, secure, explainable indoor localization solutions from Wi-Fi signals. Our research goes beyond accuracy to deliver high-fidelity localization and tracking while addressing aspects like changing buildings, signal drifts, attacks, explainability, and federated continual learning scenarios. Every mobile and edge device is typically fighting a battery and compute budget. We build AI and middleware-based resource managers that stretch both, recently including reinforcement learning for task offloading in edge fog environments. Autonomous vehicles must interpret complex scenes under strict timing and energy constraints. We study in our lab camera, LiDAR, radar fusion, sensor placement, model compression, and real-time execution on heterogeneous automotive platforms. These projects typically combine machine learning, optimization, embedded implementation, and evaluation with realistic driving data. Connected and autonomous vehicles also tend to open a new attack surface, the in-vehicle networks, that were really never built with security in mind. So our work, including Tenet and Indra, are AI-driven anomaly and intrusion detectors for these types of automotive cyber-physical systems. Last, let's look at the biggest scale, data centers and high-performance computing. These systems power cloud services and AI, but they must balance performance and reliability with substantial energy, carbon, and water impacts. So effective management starts with accurate models. We predict with our models how workloads, server variations, interference, and thermal conditions affect performance and energy in large-scale computing systems. Our recent work even questions whether cooler is always better, because aggressive cooling can consume more facility energy than it saves. What we're really seeking is the best operating point for a complete system. Funded through the Department of Defense and Oak Ridge National Lab, we've had this decades-long line of work that does dynamic voltage frequency scaling and consolidation-aware resource management for heterogeneous large-scale computing clusters under deadline and energy constraints. This work has established principles that continue through our newer projects, including how to make decisions that remain useful as operating conditions change. At the extreme scale, failures are part of a normal operation. We actually have failures occurring every few minutes and sometimes even every few seconds. Checkpointing, recovery, and redundancy improve reliability, but they add performance and energy costs. So we model when each technique is worthwhile and how runtime management should adapt, because the best choice at a small scale may actually fail when we reach exascale complexities. Geo-distributed clouds typically operate data centers with different electricity prices, renewable availability, and server capabilities. Our resource managers decide where and when workloads should run. The challenge here is to coordinate the fleet while accounting for transfer costs, delays, and local capacity. Sustainable operation also involves more than electricity. We optimize carbon emissions, water usage, cost, and service level objectives together. Because these goals tend to conflict, the result is often a set of trade-off solutions rather than one universal answer. So here, learning and evolutionary optimization helps us search through this very complex design space efficiently. And lastly, large AI workloads make addressing sustainability concerns urgent. We schedule language models and graph analytics workloads, and they're serving across cloud and edge infrastructure while balancing response time, throughput, cost, carbon, and water usage. Here, multi-agent learning is very useful as it helps us to adapt to changing workloads and resources while meeting explicit performance goals. So that's the lab. 3 skills, 1 mission. If any of this interests you, I want to hear from you. I'm looking for master's and PhD students who are interested in research. I do have several funded PhD positions open right now. You can find videos and papers at my research site or email me directly. Both of them are on the screen. And if you're picking classes, I teach several courses related to computer architecture, embedded systems, and AI. And each of them connects straight into multiple of the research areas that I've talked about. I'll close by recognizing the people and organizations behind all of the work that we do. Over the past decade, the lab has received more than $10 million from industry, from private donors, from federal agencies, and that has been extremely useful. We've also had close to 30 PhD students, more than 40 master's researchers, and over 100 undergraduate researchers. and many different collaborators across industry and across academia. So thanks for watching. If your interests connect with the problems I talked about, please feel free to reach out.